Hello all, my name is Marko E. I come from University of Oulu, and the title of my presentation is Over-the-Air Testing of Future Devices. This presentation is based on research which has been conducted over the years at University of Oulu. I would like to thank you all of my colleagues who have contributed in the research which is based on the presentation which I'm giving. So, this is the overview of my talk. First, I will discuss our frequencies for 6G, which will be deployed for extreme data rates systems. And those will be significantly higher than current 5G systems. And then one of the topics which differentiates for 6G from 5G is the usage of sub-THz frequencies, which I will also cover. One of the system what is currently already used in the millimeter wave 5G is the phased arrays, and alternative system for 6G is for use of lens antennas. Measurement of all of the radios first start with the conducted measurements, and I will briefly cover also that one in the presentation. Measurements of any radio start with conducted measurements, which will turn to over-the-air measurements or OTA measurements when the antenna has been implemented and integrated with the radios. One interesting topic of the sub-THz communication is that wavelengths of the operational frequencies will get significantly shorter, and thus new phenomena will be faced with the sub-THz communication systems. Of the generation of telecommunication standards, each generation have introduced new challenges for radio or RF testing. The first generation was based on analog FM modulation, and at that time all mobile terminals were operated on one single frequency. At that time, classical analog RF measurements were enough for RF testing and measurements. The 2G changed the communication to digital modulations, and dual-band radio networks were introduced. At the 3G systems, those were based on code division access or CDMA. The RF measurements were changed radically at that time, since communication signals were at very low level, and those were buried under terminal noise, and measurements need to be performed under a negative signal-to-noise ratio. The 4G changed the modulation to orthogonal frequency division axis, or OFDMA. OFDM spreads communication signal in time domain and frequency domain at the same time. Such signal reuse blocks are distributed multiple subcarriers, and those lead to increased signal-to-peak ratio or crest factor. The 4G systems were deployed previously operative frequencies as well as new frequencies, and thus leading to frequency support expansion at mobile and base station as well. The 5G systems continued to similar path as 4G, and it added new feature of 5mm wave networks. Those networks can be deployed starting from 24 GHz until to 71 GHz. The 5G millimeter wave systems require antenna arrays to be implemented both ends of the radio link. Number of the antenna elements in such arrays can be hundreds of the antennas, and a high number of conductive measurements of interface is not practical or physically feasible. Physical limitations actually influence the 5G standardization, and it changes from conductive validation testing to OTA validation testing. The 6G systems will deploy the same frequency allocations as previous telecom generations, and extreme data systems will be deployed over 100 GHz frequencies. Such 100 GHz frequencies will limit the possibility of conductive testing, and 6G systems will be tested and specified with OTA standards as well. If spectrum allocation of the USA is taken as an example, we may see very crowded frequency allocation up to 300 GHz frequencies. If and when 6G extreme data rate communication systems would require a significant amount of the spectra, only way is them to operate over 100 GHz frequencies. Current telecommunication networks has been deployed mainly below 6 GHz, but those frequencies are practically congested. Highest 5G data rates are available at millimeter wave frequencies, but deployment of such networks has been slower than earlier anticipated. The Wi-Fi system has traditionally used 2.4 GHz and 5 GHz frequency bands, and then there are two higher frequency options as well for Wi-Fi. The first one uses 60 frequency band, and the second one can be deployed from 250 GHz up to 320 GHz. One option for 6G communications networks is to co-locate and cooperate at the same frequency band as a Wi-Fi system, and this has been already done with 5 GHz Wi-Fi and LTE LAA as well. The 5G millimeter wave system was the first telecommunications standard which was specified with over-the-air means. Previous generations, OTA measurements were mainly done by operators to verify their mobile terminal operation in their network configurations. The 5G millimeter wave or FR2 standard requirements and verifications both are now done with OTA measurements, while the 5G sub-6 GHz or FR1 is based on conducted measurements. High-frequency 6G system will operate even shorter wavelengths as a 5G millimeter wave, and thus the physical controls are even harder. For example, 6G system at 300 GHz has a wavelength of 1 mm, while 5G millimeter wave system operated at 30 GHz has wavelength of 10 mm. The 300 GHz 6G system requires equal amount of antenna gain to boost the RF signal level. If 100 gigabits per second data rate is needed up to 100 meters, then total of 80 dB antenna gain at the radio link level is needed with current RF component technologies. The 40 dB antenna gain essentially narrows down the physical RF signal beam down to 2 degrees width. If this number is compared to current 5G millimeter wave signal beam width, then 5G has 5 times wider RF beams. The RF beam steering and tracking will be one of the significant research topics which need to be solved before commercial 6G sub-terahertz networks are in the operation. There are two main antenna topologies that can be used to increase antenna gain to the needed level. The first implementation relies on antenna lenses which focus and narrows the RF beam width at the far field of the antenna. Such antenna lenses has been simulated in 3D electromagnetic simulator. The 30 dB antenna gain requires a silicon lens antenna of 20 mm diameter, while the 40 dB antenna gain can be achieved with a 40 to 50 mm antenna lens. Alternative approach is using phased arrays like in 5G millimeter wave system. However, 30 dB antenna gain requires 1000 antennas and RF transceiver each of these. 40 dB requires already paramount of 10,000 antennas and RF transceivers. The advantage of phased array is the wider beam steering capability compared to a fixed lens. The extreme 6G data rate systems require substantial frequency support from the radio solution. It has been envisioned that a 6G system could support even 1 terabit per second data rates. The RF bandwidth of the signal is dictated by use modulation or how many bits per hertz it can transmit. Analog baseband bandwidth is half of the RF signal bandwidth if IQ receivers are used. As an example, if 200 gigabits per second data rate is needed for the 6G system, then the 50 GHz analog baseband signal is needed with the QPSK modulation. Then the 6G analog baseband signal already covers all current 5G millimeter frequencies as well. The RF transceiver development starts from the IP block designs, where each main RF transceiver block is individually designed and tested. Sub-terahertz RF ASICs are tested at probe station with waveguide probes connected to frequency extenders. The frequency extender expands the frequency support of the RF measurement instrument beyond the native operation of the equipment. When all RF IP blocks are integrated in a complete RF transceiver, then the OTA measurements will take over. The conductive measurements will be needed for debugging phase of the IP blocks, while the OTA testing is a system-level testing where the debugging of the operation of individual blocks within the transceiver is no longer an easy task. The terahertz and sub-terahertz radio testing relies on the usage of frequency extenders, which enable current RF measurement equipment to be used for future 6G purposes as well. RF signal routing on coaxial cable is practically limited up to 100 GHz frequencies. Low attenuation signal at high frequency is done with the waveguides, but those are rigid and limits the flexibility of the measurement system significantly. The calibration of the RF probe measurements is needed to be done in multiple phases so that the calibration reference plane is accurately positioned on the needed location. The accurate RF measurements with the frequency extenders are significantly more challenging than operating RF equipment with the native support frequencies. As an example, noise figure measurement results of 240 and 290 GHz low noise amplifiers are shown here. It can be seen from the result that simulated response is a flat line, while the measurement contribution to results is substantial. Similar unwanted measurement system contribution to the results has been seen also for other measurements as well. The waveguide components will introduce physical limitations to the measurements, and in worst case, those will limit the feasibility of some measurements totally. Radio link performance optimization is a multidimensional problem where multiple different parameters has own effect to the radio performance. For nearby operations, linearity of the receiver limits the performance or how close the link ends can be each other. On another side, noise figure of the receiver limits the range of the link. At optimal region, multiple radio parameters, for example, transmitters and receivers noise levels and local oscillators phase noise will limit the best achievable radio performance. The OTA measurements are typically done at the far field condition of the antenna, so that incoming RF signal is a planar wave. This improves the reliability of the measurements. However, far field distance is inversely proportional to the wavelength of the operational frequency. When the operational frequency increases, the far field distance of the measurements goes further with the fixed antenna size. The far field distance is squared proportional to the maximum dimension of the antenna. The photo shows 5G mm radio unit beam pattern measurement, which is done at a 2 meters distance, which is at the far field of the antenna array. A silicon lens antenna is an attractive option for the 6G high-frequency radios, which are operating from 100 GHz to 300 GHz. The far-field distance of different sizes of silicon lenses has been calculated. For 10 mm lenses, far-field distances are 6 cm for 100 GHz and 20 cm for 300 GHz. If the antenna size is increased to 40 mm, then the far-field distance are 1 meter for 100 GHz and 3 meters for 300 GHz. If the lens antennas are compared to euro coin sizes, 10 cent coin is the same size than 20 mm silicon antenna. 20 mm lens antenna at 300 GHz gives about 30 dB gain, while the 40 mm lens gives about 40 dB antenna gain. The 10 or 20 mm antennas could be integrated into future 6G mobile terminals, but the 40 mm lenses are mainly for base station applications. The antenna size and antenna gain are interrelated parameters, and this is illustrated with the following calculation. If 10 cent euro coin size antenna with 30 dB antenna gain is measured at 300 GHz, then the far field distance is 75 cm, as shown with the gray circle on the left figure. 75 cm line of sight path loss at the 300 GHz is 80 dB, and thus we are effectively losing 50 dB dynamic range at the far field distance. This example highlights that OTA measurements at 6G high frequencies will suffer with the limited measurement dynamic range. This will be a challenge for coming 6G standard-based measurements, which are solely done with over-the-air methods. The radio link's overall radio performance can be described with the system-level error vector magnitude or system-level EVM, which combines transmitter and receiver signal qualities into one parameter. The system-level EVM is not standardized parameter in 3GPP specifications, since the mobile and base stations are individually standardized. The system-level EVM can be also used to define radio beam width which support specific modulation. The figure on the left presents the signal performance when it is there 4 degrees from the right of the broadside direction. As an example, 5G millimeter wave radio has been used. It can be easily seen from the link level performance, and it is limited if both ends of the radio link are too close to each other, and this is visible at the bottom of the figure with the yellow color. The best performance is achieved at the middle of the beam, where the signal level EVM is lowest and it is marked with the deep blue color. The system level EVM based radio beam width differs from the half power and first null beam widths, and the system level EVM beam width is the most realistic beam width which can be used for cell coverage analysis. If the radio signal is steered over beam steering angles, the full coverage of the cell can be constructed. Both figures are present the same results but in different format. The figure on the left shows the signal quality over the signal levels, while the figure on the right converts the signal levels to coverage distance. It can be seen from the coverage figure that fine-grained beam steering is needed so that constant cell coverage and range is achieved. When the operational frequency gets higher, wavelengths of the signal get shorter. Effect of the finger has a substantial at high frequencies, but at low frequency it has no effect at all. If the 6G system operates at 300 GHz, finger is actually a large electrical object. If the finger's width is 1.5 centimeters, then it corresponds to 15 wavelengths. Large size 1 will have the same effect for the radio signal operated at 700 MHz. The same 15 wavelengths objects at different 5G frequencies are shown in the table, and for example, at below 2 GHz, car-size objects are needed for the same finger effect as 300 GHz. The finger effect on 300 GHz radio link has been studied and measured with the hand phantom, which was moved along and across the radio link. RF measurements were performed with the signal network analyzer. RF measurements and hand phantom movements were synchronized to enable easy measurement result analysis. The finger phantom was changed to other material objects as well, and interesting results were noticed. The finger acts as similarly as an iron and stainless steel rods, but the copper stripes are almost invisible for 300 GHz radio signal. Most interesting result was that if a nylon rod was used, then it acted like a radio lens when the radio beam was at the middle of the rod. In this situation, it boosted the 300 GHz signal by 3.8 dB when it traveled through the nylon rod. Based on these results, one may say that a 300 GHz radio signal will face very different propagation environment compared to 5G signals.
But there will be also significant differences as well. If and when 6G will need to support hundreds of gigabits of data rates, then the RF bandwidth will be significantly enhanced, and those will be even higher than 5G systems what we have already used. The high-frequency 6G systems will be standardized over the airman as 5G millimeter system at the moment, and those will be also face the similar challenges what they have at the moment. One of the major challenges for upcoming measurements is that we will need to use the frequency extenders, and we will need also characterize those before doing the actual measurements. One of the topics which need to be solved is how we can generate good quality measurement signals, and all of those need to be also very wideband as well. High frequencies where 6G will be deployed for extreme data rates will have a significant line of sight path loss, and that will reduce the dynamic range of the measurements. Last but not least, new coming 6G extreme data rate systems will be much more costly than current 5G measurement systems, and those need to be also taken into account when thinking about doing the measurements and testing. Following publication has been used as a basis for this presentation. This concludes my presentation, and thank you for watching.